Professor Maharshi Thakkar on behalf of the Mechanical Engineering Department of A.D. Patel Institute of Technology, Constituent College of CVM University, welcomes you all in this short-term training program, which is online on Applied Computational Fluid Dynamics for Automotive, Space and Defense sector, scheduled from 1st to 5th March. Actually, this is the third phase of this training program on computational fluid dynamics. The first was on fundamental computational fluid dynamics, which was held on December. The second was on the CFD of renewable and hydraulic machines domain. And this is the third phase, which is dedicated to automotive, space and defense sector. So if anyone have missed those previous two sessions, can find that on ADIT's YouTube channel. So I welcome you all in this particular short-term training program. Our speaker has joined. And now I would request the principal of A.D. Patel Institute of Technology, Dr. Vishal N. Singh sir, who is also the coordinator of all this short-term training program on computational fluid dynamics, and who has inspired us and motivated us to say schedule and nicely coordinate all these programs. So now I'll request the principal ADIT, Dr. Vishal Singh sir, to bless us with the few words.
A very good morning to all and greetings to all the participants. We welcome you all on behalf of ADIT, a constituent college of CVM University. We are located in central Gujarat, the birthplace of Sardar Patel. We have been promoting events like this in different domains. More than 200 participants have enrolled for this particular third phase CFD program. As Maharshi has already mentioned, this program is third in series of STTPs on computational fluid dynamics, which has emerged as one of the important tools for the simulation, which helps us reducing the cost of the prototyping and helps us evaluate various options for different systems. We have esteemed speakers from different institutes of national importance. I hope over next 5 days, all of you will be benefited by their knowledge and wisdom that they share. And this STTP will go a long way in creating your interest in this particular domain. The videos will also be available on ADIT YouTube channel for your future reference. Once again, I welcome all of you, and I especially welcome today's speaker, Mr. Sunil. So thank you, sir. With this, I would request coordinators to begin the program. Dr. Mitesh, Mr. Maharshi, they have really put in a lot of effort. I would also congratulate Dr. Y.D. Patel, head of mechanical department, who has again contributed a lot for the success of this program. Thank you and all the best.
Thank you very much, sir, for your kind words and the appreciation. Now I would request Dr. Y.D. Patel, sir, the head of Mechanical Engineering Department of ADIT, to say a few words.
A very good morning to all. It's my pleasure that there are more than 200 participants in the third phase of this CFD faculty development program. I will just brief about the department. The department is established since 2000, and department has young, energetic and dynamic 21 faculty members. Department has state-of-art laboratories. We have invested more than 5 crores in purchasing the state-of-art equipments and machines. More than 250 publications by the faculty members as well as students in the national and international journals, as well as national and international conferences. Department is regularly organizing different STTPs, faculty development programs, webinars on the emerging technology, entrepreneurships, innovation and startups in support of forthcoming new educational policy announced by the Government of India. There are more than 40 students among the 120 are always opt for the higher educations at the institutions like IITs, NITs, as well as the foreign countries like Canada, USA, Germany, Netherlands, and Australia. Department also runs the 3 PG programs in CAD/CAM, thermal engineering, and renewable energy. Now, once again, I welcome all the participants to visit and welcome at the Mechanical Engineering Department of ADIT campus. I am sure that all of you have a fruitful interactions during the STTP with the eminent personalities. As Principal Sir has mentioned that we have tried our best to call upon the eminent personality from the IITs, NITs, and all the institutes of the national importance. So once again, I welcome you all, and I also congratulate the coordinators, Dr. Mitesh Shah and Mercy Thakkar, for their efforts for behind this STTP. So thank you very much.
Thank you very much, sir. Now I would like to request Dr. Mitesh Shah, sir, who is also the co-coordinator of this entire journey of Computational Fluid Dynamics short-term training program, and is the professor in Mechanical Engineering Department, to say few words and blessed us with his few kind words.
So, very good morning to all participants. Greetings from AD Patel Institute of Technology, Department of Mechanical Engineering. It's a constituent college of Charotar Vidyamandal University, located in New Vallabh nearby Milk City, Anand of India. Basically, this program was sponsored by All India Council of Technical Educations under the scheme of AQIS. So as Professor Maharshi mentioned that there were 3 different phases for this program, and all these 3 phases are related to the computational fluid dynamics. So Institute has divided these 3 phases in a different manner. The one which will be the applied computational fluid dynamics for the engineers, where very renowned faculty delivered that talk, like Professor Atul Sharma, Professor Date from IIT Bombay, Professor Suman Chakravarti from IIT Kharagpur. Like that, many faculty members, many researchers, those who are working in computational fluid dynamics since long, they delivered their extraordinary talk during their sessions. The next session was related to the computational fluid dynamics for renewable energy and hydraulic machines. So basically the theme was renewable energy and hydraulic machines. So where we have invited various speakers from the industries like Crompton Greaves, then after you can say Kirloskar, etc. So industries people were also involved in that particular session. Now the last session was, which is related to the CFD analysis for the auto, space and defense sector, where you will find the speaker from IIT Kharagpur, IIT Kanpur, IIT Dhanbad, VJTI, etc. If you see the list of the participants, very huge response we got in this particular STTP. Not only that from the Gujarat, but we got the response from the VJTI Mumbai, NIT Calicut, similarly Vellore Institute of Technology. Like that, many renowned institutions, participants are also involved, and they are helping us in attending this particular short-term training program. So far, in all this particular short-term training program, 28 speakers delivered that talk in the previous 2 sessions, and in the current sessions, 14 more speakers are going to deliver their talk. As Professor Maharshi mentioned that 260 participants already registered and 150 have given their final consent for attending these particular sessions. I am pretty sure you will enjoy all these 14 sessions, and you will learn something at the end of the STTP. Once again, welcome you in this short-term training program. Thank you very much. I request Professor Maharshi to go further for the next agenda. Thank you.
Thank you very much, sir. Now, as per our tradition, before starting of any occasion, we remember Almighty God for their blessing. So, I would like to play prayer prepared by the ADIT prayer team. So may God bless us in this particular short-term training program. Now, I would like to introduce our today's speaker. Our today's speaker for first session is Dr. Sunil Manohar Das. He is the Assistant Professor in Department of Aerospace Engineering at IIT Kharagpur. Sir has completed his PhD from National University of Singapore with a CGPA of 4.58 out of 5 in December 2014. He has completed his BTech from National Institute of Technology, Rourkela, with an CGPA of 9.34 out of 10. Regarding his work experience, he is working at IIT Kharagpur as an assistant professor since April 2018. He is involved in the research work on bluff body aerodynamics and flapping aerodynamics, and setting up the water tunnel experimental facility and flapping aerodynamics laboratory at IIT Kharagpur. Sir has also worked at IIT Dhanbad for the period of December 2017 to April 2018 in the Department of Mechanical Engineering as an assistant professor. He has also worked as a research fellow from January 2017 to December 2017 at Singapore University of Technology in Singapore. Regarding teaching experience, sir is having more than 8 years of teaching experience. He is having 16 international journal and 9 international conference publications. Regarding achievements, he has received National University of Singapore Research Fellowship for the year 2010 to 2014. He has received Best Conference Paper Award in the Fluid Mechanics session in the conference RIDME 2018 held at Shillong, Meghalaya. He has also chaired the conference session on aerodynamic study in ICAFM 2016 Malaysia, on active flow control in 17th DFD meeting, and on fluid mechanics in RIDME 2018 at Shillong, Meghalaya. He has also working as a reviewer of many international journals. He is honored with a gold medal from Institute of Engineers India for Best Mechanical Engineering Graduate of the Year 2009. Also, he is honored with an Institute Silver Medal from National Institute of Technology, Rourkela, for Best Mechanical Engineering Graduate of the Year 2009. Sir, we are pretty fortunate to have you as a speaker in this short-term training program. Now I will request you, sir, to start your presentation.
Thank you, Professor Thakkar. I'm glad to be here and part of your STTP program. And it is my honor to deliver my lecture on flapping aerodynamics. I will come to that shortly. Let me share my screen. Okay, am I audible to all of you? Can someone please respond?
Yes, sir, you are audible. You are audible.
Okay. So as you can see, my topic of today's discussion is propulsive performance of the two-dimensional flapping aerofoils. So like the current STTP program is mostly focusing on applied computational fluid dynamics in the sector of defense and automobile and other things. So this will be one of the interesting area that you can find out in the defense related applications. Like flapping aerofoils are mostly used or seen in micro aerial vehicle as well as in underwater vehicles. So here I'm going to talk about from the underwater vehicle perspective, and particularly my discussion will be limited to two-dimensional aspects. So like already Professor Thakkar has introduced about me, more details you can find about my research team and all in this web page, and you can always write to me via this email ID. So we'll be happy to address your consent, and if you want to do any collaborative research work, we can go ahead. So let me, so this will be my outline of today's presentation. And at first, let me introduce to you about IIT Kharagpur. I think some of you might have visited IIT Kharagpur earlier, or if not, then this will be a quick introduction about IIT Kharagpur. So as you know about IIT system, like right now we have more than 23 IITs across different part of India, and IIT Kharagpur is one of the oldest one. So you can say that this is the mother of all IIT. This was established in 1951 and has more than 12,000 students and more than 700.
But your slide is not changing.
Oh, sorry about that.
Now it is changing. Yeah. And kindly do full screen, sir.
Is it? So I am actually presenting in the full screen mode. Can you see the full screen, or is it okay now?
Press F5, sir.
Yes. Okay.
No issue, sir. No issue. You can continue, sir.
Slide is changing?
Yeah, it is on third slide now.
Okay.
Okay.
Okay. So as I was mentioning about IIT Kharagpur, so there are more than 1,200 students, and we are here more than 700 faculty members. About the discipline, what we offer, more than 60 educational discipline, including medical sector, agriculture, and MBA, etc. We cover the different educational disciplines, and it is one of the largest IIT, and it spread across around 2,100 acres, or equivalent to 8.5 kilometers squares. So the nearest metro station, Kolkata, from which you can always get trains to Kharagpur at any time in the day, or you can hire taxi as well. So this is the oldest building what we have started with. So this was earlier established by the Britishers, and it acted as a prison cell also. Like Sir Pandit Jawaharlal Nehru was also here for a couple of days. And you can see the structure was built based on a watchtower. Okay, since I said this is a prisoner cell, so they have a watchtower here. So we have this building as it is right now also. Previously it was our old main building. Now we have shifted to a new one, which is a new main building. And this is also quite establishment of this new building is already more than 30 years. And we were...
Hello, sir.
Yes.
Your slide is not changing, sir.
Again.
Now it is changing.
Probably reason is this.
Now it's like when I go out of the full screen, it is changing, is it?
एक्चुअली सर फुल स्क्रीन नहीं हुआ है अभी तक. इट इज अगर आप स्लाइड शो में जाके फुल स्क्रीन
let me reshare. Yes. Okay. I'm doing a window share. Okay, now you can see the slide, right?
Yes, sir. Your presentation is coming now. Your
Slide. Now the whole screen. I think there is some issue with the internet connectivity. Probably that is. Is it visible now?
Presentation is visible, sir. Just go to slideshow and make it full screen if possible, sir.
I am in the full screen mode right now on my system here. I don't know why it is not.
No issue, sir. No issue. Yeah. You can carry on, sir.
Okay. So this is the new building. Apart from, so I'll just like to show you some of the featured blocks in our IIT system. I hope the screen is visible to you. If not, please interrupt me anytime so that I can make the content.
Sir, I request to change your slide so that we can check once again, so that we don't have to interrupt you once again.
Okay. So is it changing?
No, yes, fine. Now it is changing. Good. Go ahead.
Okay. But this will be in the not. It is not in the full screen mode. So that is.
No
I
issue.
have couple
But it is
of
visible to us, so no issue.
Okay, sure. Okay, so let me shorten this one. All right. So we can.
That's good. That's good.
Okay, you can see we have several other buildings. Like this is a School of Management, which is newly established. We also have School of Medical Science and Technology, and this particular school has developed various medical devices. Like Professor Suman Chakravarti, I am glad to hear he presented during the previous sessions. So he is a part of this school, and they have developed recently a new COVID detecting devices, which is low cost as well as currently being used in detection of the COVID, and it has a 95 or more than 90% success rate, I will say. The detail you need to find out from the publications and all. So this is one of the goods. I mean, so the research work coming out from this school is quite well known. And we have also law school here, Rajiv Gandhi Law School. So that deals with different aspects of the IPR related issues. We have big auditoriums where the students as well as the audience can be accommodated. More than 1,000 seatings are available, and there are various auditoriums like this. We do also have open air theater where the performance and movie screening also happens, and the capacity is also quite big. And this is the department where I currently work. Department of Aerospace Engineering, IIT Kharagpur, and most of my research work happens in the Aerodynamics lab. Okay, where my research lab is also there. So you can see about my research lab. This is BIAH research lab, which is bio-inspired aero hydrodynamics research lab. I will come to that subsequently. So yes, now some of the facilities that we have in our aerodynamics lab. This is industrial wind tunnel. You can see it's quite big, and about the test section size, if I would like to say, the test section wise it will be 2 x 2 meter, and lengthwise it will be 6 meters. So it is quite big, and we do various research like starting from railway, building aerodynamics, all those research we carry out in this industrial wind tunnel facility. Apart from that, we also have low speed wind tunnel where we mostly carry out the UG labs as well as few low speed aerodynamic experiments in this. We do have PIV setup to carry out the experiment and flow visualization using the PIV technique. I am sure some of you might have heard about this technique, particle image velocimetry, where we try to visualize the flow field using laser technique. So we have that setup, as well as we have high Mach number wind tunnel facility where we can observe supersonic flow, and this facility is there from more than 30 years already. So we do supersonic experiment and measurement on this. So my research team recently has developed this water tunnel facility in IIT Kharagpur. So you can see that we have established this particular water tunnel, which can be used for various MAVs and UAVs. So MAV is micro aerial vehicle application, and AUVs is autonomous underwater vehicle application. Where we can see that the tunnel facility itself is quite good, as the turbulence intensity level is less than 2% and uniformity is more than 99%. So we are having some of the experiments already started here. So this is a recent addition to the lab. And this is about the bio-inspired Aero Hydrodynamics research lab. Like the principal investigator is being here. We have several research students, PhD scholars, as well as master and JRF students here. We also do have the eminent professors as our research collaborator, like Professor Michael Triantafilo from MIT, USA, and Professor Pablo Valdivia from SUTD, Singapore. And then Professor Lua Kimbun from NCTU, Taiwan. So there are a few more eminent professors who are currently working with our team. And so major thrust areas that we are working on. So actually I have some of the videos here. I hope it can be seen. So major thrust areas that we are working on here is one of the areas is flapping aerodynamics. So I will come to details of this. So here what we are looking for is how we can develop autonomous underwater as well as aerial vehicle using the bio-inspired principles, like following the biomimetics of the natural swimmer, like fish, different type of fish, and also natural flyers like birds or insects. So we are trying to develop different type of MAVs and UAVs using their locomotive principles, and try to find out how we can enhance the propulsive performance based on considering different aspects, like for example considering the different fin shape as well as different perseverance on the leading edge and trailing edge side, so whether they are beneficial to us or not. So those are the areas that we are currently investigating. Apart from that, we also have our team is also looking after this blob body aerodynamics. Like I have said, blob body aerodynamics is one of the key areas that is many professors are working in aerodynamics lab in the Department of Aerospace Engineering. So here we are looking for two main aspects. One of the thing is to characterize the flow physics behind different type of blob bodies, starting from the vehicle, truck or car type of shape, or going through a traditional type of vehicles like square cylinder and circular cylinders. And also the second aspect what we are looking for is how we can control this unsteady wake structure. Like you have already maybe aware of this fact that when there is vortex heading behind the bluff object, it may leads to fluctuating kind of forces. Like you can see here, there will be due to the force fluctuation, the structure may vibrate. Okay, so this is one of the vortex induced interaction that had lead to previously this breeze has collapsed, and this is already well known in I think most of you might have seen this video. This is Tacoma breeze collapse, then that happened due to this unsteady flow pitches in the downstream. So one of the area that we are targeting is how we can avoid this unsteady flow pitches by providing various active and passive control measures. So we are looking for different active control measures, like you have seen here, compliant surface and moving compliant surfaces. Then we have also rotating cylinders, which are also shown here. And these are, you can see that application wise, we are considering computational fluid dynamics as well as the experimental fluid dynamics. So instead of just going into the details of any solver development, here I am trying to focus on different aspects of the application of the CFD that suits the current HTTP program. So here you can see that we can achieve actually a significant amount of drag reduction by having these control measures, like more than 70% also we can achieve using these two techniques. There are various other techniques that we are also looking after, and these data are already available in the form of publication. You can go through, and I'll be happy to take some of the future questions if you have. Another area that we look for in blubber aerodynamics is building aerodynamics, where we talk about the comfort level of the people or residents in a particular location. So here you can see that we have designed a structure, a pavement type of structure, and which can be used in the bus stations or the train stations. And there we talk about how the flow field actually happens in and around this structure, and whether it is going to be comfortable to the people who are passing by or living nearby those locations. When these are the flow physics analysis what we have done on this particular study, and this work was also presented in one of the media features in Singapore. So we did both experiments as well as simulation, and the details, if someone is interested, can go through our articles. Apart from this blubber aerodynamics, we are also looking for development of underwater vehicle, like I have mentioned, and this is the other aspect we are looking for is a jellyfish kind of underwater vehicle, because we know that the jellyfish is quite maneuverable creature. It can maneuver in a small space, and it has a unique type of propulsion technique. So we have designed our own robot based on taking the locomotive principles of jellyfish, and here you can see a 3D model of that. And here using the contraction phase and the expansion phase, we can actually get the propulsive motion of our robot, and we have filed a patent for this and currently waiting for the result. Yes. Also also in another areas that we are currently looking for is the development of alternate CFD solvers that can be used or overcome the traditional Navier-Stokes solutions or finite volume, finite element, that type of solvers. So here, what is the uniqueness? Like you can consider this simple problem statement. If we have the object moving, if we have
Hello, sir.
Yes.
So your slide is not changing.
Okay, now is it okay?
Could you change just one slide so I can confirm?
Is it changing now?
Yes, sir. Now it is changing. Yeah.
Okay.
Okay.
Yes. So we are developing the new CFD solvers. Here, basically, this is a mesoscopic solver. Like instead, you must be knowing about Navier-Stokes solvers, which are macroscopic, like continuum assumption is valid. In mesoscopic, also continuum assumption is valid. But why we are developing this alternate solver? This has a specific advantage for the moving boundary type problem. Like you can see, if I consider an object is moving in a fluid domain, for example, this particular aerofoil here, if it is oscillating in an domain, then I need to change my mesh, and every time it moves. Okay, so because of that, all the results I need to project to the new mesh in every time step, which is very much time consuming, and solution wise it may take higher computational resources and the computational time. So to avoid that, we are developing an alternate solver where we try to fix the fluid domain and we just move the solid domain as it is shown here. And instead of solving the Navier-Stokes equation, we solve a different particle based equation, which is called as Lattice Boltzmann equation, or which is basically derived from the Boltzmann solver. So here what we do, we represent the fluid in terms of fluid particle. Okay, so taking the average of the fluid particle or the particle density, which is defined as F, and we try to see their streaming as well as collision. Streaming means when the particle moves to the next cell, and the collision, once the particle has moved to the next cell, it collides with the existing particle at that location. And based on that, we try to see whether the momentum and the mass conservation is happening or not, even the energy conservation. So once everything is ensured, then we can actually derive the different fluid properties, like your density term, viscosity term, pressure, and the fluid parameters like the velocity. Those can be obtained from the governing equations. Okay, so I will not go through the detail of this. These are some of the validation study from our present solver. Like you can see, we have solved the conventional flow path circular cylinder, and as well as the lead driven cavity in an inclined manner. We also have simulated this moving on problem.
Excuse me.
Yes.
Again, your slide is not changing, and you are requested to move your cursor so that participant can able to understand what you are talking currently.
Can you see my slide now?
Now, yes, currently you are showing some results from our developed LBM solver, latest Boltzmann method.
Yes, yes. But when I go to the full screen, is it still visible or no?
No, it is not full screen currently. But now we can easily see what you are presenting. But you are requested to move cursor on the screen so that people will understand.
Sir, please use any red color so that we can. Please use any red color so that we can understand that which line you are actually teaching, sir.
Okay, let me. Can you see my cursor now?
Yeah, cursor is visible. Cursor is visible.
Sir, any color you use, a red color, sir, so that that is very easily to understand, sir.
Okay, yeah, Mr. Nirmal, but actually, sir is not in full screen, so it is difficult.
Yes, that is not possible to do without any full screen. So okay, so yeah, so these are some of the results. These are properly validated with the previous data. Now coming to the present talk, which is on the investigation of the propulsive performance of 2D flapping aerofoil. Let me give you a brief idea. Why do we need this particular study? What is the motivation behind us to carry out this particular research? Like you can see that on an Indian map, the Indian coastline is spread across more than 7,500 kilometers. You can see that it's a quite large coastline. So in order to claim and hold and utilize the ocean properly, and for the security reason as well as the conditional monitoring in this particular area, we need to have high efficient autonomous underwater vehicles. Excuse me. So there are various autonomous underwater vehicles are already designed, but what we are looking for is how we can improve its performance in terms of its efficiency, and whether we can provide any new way of designing the underwater vehicles based on the investigation or the data what we obtain. So that is our objective behind this particular study. So like I have mentioned, we are the design of the underwater vehicle is inspired from the fish. For example, here, if you can see, I hope you can see the GIF file here. So there are two fish I have shown here. One is shark and the other one is hammerhead shark. So they actually do their propulsion based on flapping of their tail fin. And this flapping of the tail fin can be seen in this particular sinusoidal manner, as you can see here. If I take a cross section of their tail fin, it will be actually seen in this way. It is basically a form of an aerofoil section, and as it moves forward along with in its swimming time, it will also have some form of angle to the direction of its motion, as well as it is propagating in a sinusoidal manner. Okay, so here if I change the frame of reference to a stationary frame, I can fix the location and I can simply oscillate the wing with having some angles. Okay, so it is oscillating and having some angles, so that these two type of motion will be considered as your heaving as well as pitching motion. When the aerofoil is pitching at certain angle, that will be called as pitching motion. This simple vertical motion will be called as heaving motion. Okay, so we are investigating this in this particular study. I will just talk about this two-dimensional aspect of heaving and pitching motion of this aerofoil. Now coming to why the aerofoil generates thrust. Okay, so here you can see that so I have considered two different objects here. One is elliptic aerofoil here, and one is circular cylinder here. So if I go to the full screen, you can see that this elliptic aerofoil produces a vortex streak, which is reverse Kármán vortex streak. Okay, so you can see here, so reverse Kármán one Kármán vortex streak. So if I do a averaging in the wake region, it will give me a momentum axis type of velocity profile, and you know that momentum axis velocity profile is it will generate a jet-like structure. Okay, so that means on an average scale, there will be a jet-like structure behind the aerofoil, and due to this action of this jet, the aerofoil will get a reactive force, and that will propel in the forward direction. Okay, so that leads to a thrust generation on the aerofoil. All right. This is different than your conventional type of vortex street, which is von Karman vortex street, where you try to see a drag producing kind of nature. Okay, where you try to see a drag producing type of nature, and the significant difference between the vortex streets are shown here. Okay, this is reverse von Karman, and this is the von Karman. And if I take an average of the velocity profile in the wake region, you can see that it will form a momentum deficit kind of situation, and because of that, this whole cylinder will be dragged into the wake. Okay, so that will produce a drag on the cylinder. Whereas in the other case, I said there will be thrust, so the aerofoil will move along the direction, forward to the direction of the flow. Okay, but this will be drag. So that is the basic principle behind how the propulsion actually can be generated using a flapping aerofoil. Now coming to the problem statement, what we are trying to investigate here is how the propulsion performance can be improved if we consider different parameters. Like for example, if we can have various angle of attack. Okay, if we can have various angle of attack and various propulsive performance based on the different flapping frequencies. So here I have mentioned the flapping frequency in a non-dimensional form. If I vary it from 0.1 to 0.8, which is true Hall number, how the propulsion performance is changing. And Reynolds number in this particular study we have kept as 5000, because in this particular range, mostly you can see that the MAVs and UAVs, they operate in this Reynolds number range. And here we are considering the aerofoil movement in a sinusoidal manner. This is sinusoidal heaving, and this one is sinusoidal pitching. Like pitching is also sinusoidal, and this is your effective angle of attack. So effective angle of attack is basically here, since the aerofoil is also moving vertical direction and there is an incoming flow, because of that you will get a resultant velocity, and the resultant angle will be called as effective angle of attack. And that we are keeping the maximum of effective angular attack we are keeping as 10, 15 and 20 degrees. And we are going to solve this particular problem using commercial solver. Here we have used ANSYS Fluent, and in ALE formulation we are going to solve this one. And these are few parameters that we have set. Okay, so I think these are not so important at this stage. So coming to the research methodology, so we have divided the whole computational domain. We have taken an O-type computational domain, and this is our inlet side, velocity inlet. This outlet is pressure outlet, and we have interior domain, and there are two interface defined, which is sliding over each other. So this inner domain is sliding over the outer domain, and what the inner domain does also, it moves vertically as well as it rotates. Okay, so if I show you the mesh motion, it will be like this. Okay, and the traditional boundary condition we have used, no slip boundary condition on the surface of the aerofoil, and we have generated a structured mesh around the aerofoil using the dynamic mesh technique. So there are a few dynamic mesh parameters also we need to input in the Fluent solver, and we have written our own in-house UDF to generate this particular type of flapping motion, heaving and pitching motion. For the experiment, we have conducted experiment on the water tunnel facilities, and you can see here it's an integrated system. The mechanism is set here, and we can control both the flapping motion through this integrated system here. So I think this is self-explanatory picture. Now coming to this particular mechanism, which mimics actually whatever motion I have said on the computational part, the exact thing can be repeated or replicated in this particular flapping mechanism. You can see here in the GIF form I have shown the real life images taken, or the real life video taken from our setup. So this is your single wing flapping, and we also have two wings here in tandem arrangement, which you can see that both are oscillating as well as it's making an angle at the same time. So heaving and pitching. We have derived not rather derived. We have developed this particular force sensor here. Pardon for the spelling mistake here. So this force sensor is developed in-house, and it has 4-bar bending mechanism. The details you can find out from our publications. So another uniqueness about our work is using the PIV or particle image velocimetry technique to visualize the also the measurement of the flow field. So to visualize as well as perform the measurement of the flow field, we have used particle image velocimetry. So here what we do, we take 2 images simultaneously and try to correlate using different type of correlation principles, cross correlation principles to be particular about. Then we obtain the vorticity field, like you can see here. We can obtain the vorticity field and we compare whether the same vorticity field is seen in the numerical simulation or not, since we know that whatever we get in the experiment, those cannot those are real and happening in the real scenario. So whether the computational technique is correct or not, you need to validate it, and this is second stage validation. Like we have validated with the force data as well as we validate with your flow physics also. Okay, so we are very particular about whether the data is correct or not, what we are obtaining. So that's why we are performing this particular PIV analysis as well. Then this is about the validation of the solver. Like I have said, we obtain the force using the force sensor, and this is one particular I think Reynolds number around 5000 and flapping frequency of 0.3 Strohal number. So we get a force data like this. This is a transient force data. So over a flapping cycle 0 to 1, you can see that in one flapping cycle we get a peak here and get another peak here. So this is your upstroke and downstroke side. I will come to that upstroke and downstroke. And what you see here, basically you can see our CFD data matches quite good with the previous publication. CFD as well as the experiments, and this is about the mesh independency test, where you can see that we have obtained a proper mesh independency here. Like the errors keep on reducing as you increase the mesh size, and I think we have followed M4 for our investigation or carry out the subsequent simulation. We have used this M4 mesh size. Now, what are the profile or the heaving and pitching profile that we have followed in order to keep the effective angle of attack profile constant, or the maximum of effective angle of attack constant? We have used heaving profile of sinusoidal one. Like you can see, this is the heaving profile kept constant. Heaving means just the oscillation of the aerofoil, and the pitching profile, it changes as I increase the flapping frequency. So this is the non-dimensional flapping frequency or Strohal number. So you can see that the Strohal number increases. By that, the pitching profile also or pitching amplitude gets modified. Okay, so this modification happens because of the definition of the effective angle of attack, like you have seen earlier. So when I try to fix the effective angle of attack at 10 degree, I need to change the pitching amplitude, and you can see higher the flapping frequency, higher will be my pitching amplitude. So I want to tell here one thing: if I am increasing the pitching amplitude, the aerofoil needs to rotate at a faster pace. Okay, if I see at a non-dimensional time scale 0 to 1, I have a larger pitching amplitude for larger flapping frequency. That means my aerofoil needs to cover this high angle and comes back to that same 0 angle in downstroke itself. So it has a higher rate of rotation, and we saw that this rate of rotation has a detrimental effect. Like subsequently you will see that this higher rate of rotation is detrimental to the thrust performance of the aerofoil, or it is detrimental to the performance of the when you're designing an underwater vehicle and on this flapping based propulsion technique you're trying to measure. So this higher rate of rotation can be detrimental, so you need to be very careful when you design it. So yeah, so that is what I want to discuss here. So yes, coming to this particular slide, you can see here the thrust performance, how it varies with the Struhal number or non-dimensional flapping frequency. You can see that, and this is plotted for different angle of attack. So 10 degree, 15 degree, and 20 degree, both CFD and experiments are data are shown here. You can see when I increase the flapping frequency, for any particular angle, you can consider, let's say, 10 degree angle of attack. So you can see that the flapping frequency increases up to certain Struhal number, then it reduces. The same happens for all other all other angle of attack also. So it increases up to a critical value, then it reduces. So that critical value is defined here, STC. Okay, and so this is in the average time average thrust performance. When you see the transient profile, what means from this transient profile, basically we have derived the time average information. So in order to detailedly investigate what is actually happening on the time average, we have come down one stage before. So we try to investigate the transient profile here. So the first half, so 0 to 0.5 is your downstroke, and the next half is 0.5 to 1 is the upstroke. So downstroke means when the aerofoil is coming down, upstroke means when the aerofoil is going up. Okay, so that is what it is showing. So you can see that in all the cases, the downstroke and upstroke, they are symmetric. Okay, so instead of discussing the results for both downstroke and upstroke, we just limit our discussion to downstroke alone. Okay, so another thing you can see here, as I increase the Struhal number, flapping frequency, non-dimensional flapping frequency, the transient CT profile changes. Okay, and this change in the transient CT profile leads to different time average values. Okay, so at the lower flapping frequency, lower in this range around 0.2 or 0.3 range, so we just see type 1 type of transient CT profile, where you just see a parabola. Okay, you just see a parabola. But when you go to a little bit higher transient CT profile, you start to see a flat edge, and then a parabola continues. Okay, so at the beginning only you have some changes. When you go for further higher, like in this range C, you start to see that you have a multiple peak type pattern. It is not only a parabola, it has some part as parabola, but it has multiple peaks. So this is peak 1 and then another peak. And if you continue further, like in this range, in the thrust deteriorated range, you can see that the peak, multiple peak profile continues, but the valley region, it increases. Okay, the magnitude of the valley region is actually enhanced. So here you can see it is nearly 0, but here you can see minus 0.75. And another thing you need to note down here is, on a time average scale, you can see that the CT values, time average CT actually is 0, or if I further continues, it will go to the negative CT. So negative CT means it's basically producing drag. Okay, so it's already thrust reducing and going to produce the drag. So we try to investigate what is actually happening. Now we know that on a force profile, we saw that, okay, time average thrust is reducing, transient CT is also getting changed. What is happening in the flow physics? So that is our next concern, like why this transient CT is actually appearing. So I'll go through the details of the flow structures, what is actually happening in different transient CT regime. So you can see that, let's first consider the type 1 type profile. So as you can see here, it's a parabola, like I have said, it's a smooth parabola. So at the whatever data I'm going to show now, it's already a periodic state condition. It is not at the beginning, it's already in the 10th flapping cycle. So you can say that this periodicity has already been established. So at the beginning, like I have marked few points from 1 to 6, you can see here. At point 1, you can see there is a leading edge vortex which was generated in the previous cycle, like in the previous upstroke. This leading edge vortex was generated, so that's why I named it as RLEV, and that RLEV is still there. It is still present at the trailing edge of the aerofoil. So because of that, you see a negative thrust or a drag at the beginning of the stroke. So because this RLEV has a suction effect which will produce drag on the aerofoil. So that's why it is showing a negative value here, but slightly negative since it is about to shed. So that's why it's a slight negative is there. After that, when the RLEV sets completely and the LEV is formed on the aerofoil surface, then it starts to increase. Okay, so then the value starts to increase or the transiency value starts to increase, and this increment continues with the increase in the strength of the LEV. So this LEV will continue to increase its strength. The LEV will continue to increase its strength, and it will spread across the aerofoil. So because of that, the transiency values will keep on increase, and it attains a peak near to its mid of the downstroke or mid of the upstroke. Since they are symmetric, so mid of the downstroke. Let's just talk about the downstroke itself. So it attains a peak here, then afterwards it reduces. So this rate of reduction or this reduction happened because the LEV has shifted to the other side of the aerofoil, like on the second half of the upper surface. So where it will start to produce a drag, okay, or a reduction in the thrust. So that's why you are seeing a reduced thrust value, and simultaneously aerofoil is also reducing its pitching angle and starting to prepare for the upstroke. So that's why this downward transiency is seen here. So this is the explanation behind parabolic tape profile. And coming to B, which is the intermediate Strohal number, where we saw the parabola profile has an additional attachment at the beginning, that is a flat edge type formation. So here also we see presence of the previous stroke leading edge vortex, which is RLEV, but at the same time what we start to see here, there is a formation of LEV. Okay, so the competition between the present stroke LEV and the previous stroke RLEV, they try to nullify each other, or they try to cancel out each other's effect, and by that it follows a smooth or flat edge type of transiency profile here. Okay, then as the aerofoil continues its downstroke, the RLEV starts to set. The RLEV starts to set, and because of that, only the effect of the present stroke LEV is seen, which continue to increase with the downstroke, like as the time proceeds, and it will attain a peak. Then afterwards, it will again reduces its or the transiency will reduce because the LEV will be shifted to the other half of the upstroke or other half of the upper surface of the aerofoil. Okay, so that's why it will reduce again, which is already I have explained in the type 1 type of profile. So this is we have considered as type 2 profile. Now coming to the thrust deteriorating type, which is type C, where we saw that at this particular flapping frequency or Strohal number, there is no positive or no significant thrust. Actually, the thrust has reduced. Something similar you can correlate if you know about the stall and the aerofoil or conventional aircraft. After certain angle of attack, the lift on the aerofoil or aircraft reduces. So something similar you can correlate, like beyond a certain critical Strohal number, the performance of the aerofoil is reducing. Here the thrust performance is reducing. So we try to see what is happening here in C. So this we have categorized as type 3 region. Okay, so in the type 3 region, you can see the flow physics is different than the previous two types. So at the beginning of the downstroke, that is T star equals to 0 at this location, you can see that we have instead of RLEV, we have a counter rotating vortex pair. So we have a positively rotating vortex here, and another one is having a negative circulation. So both of these will produce a resulting induced velocity on the aerofoil in this direction, like I have shown here, in the induced velocity along this direction, which is along the thrust direction. Okay, and there is also simultaneously formation of a LEV. Okay, so because of that, you start to see a straight increase in the transiency profile from the very beginning of the downstroke. Okay, which is very much different than the previous two type what we have discussed. So because of the combined effect of the LEV and the induced velocity effect of the counter rotating vortex pair, we start to see a positive rise in the transiency value. Now when we proceed in the downstroke, we start to see that this induced velocity effect actually is suppressed, or it is actually totally neglected afterwards, because the location of this induced velocity will move as the this LEV structure, RLEV structure is moving on the lower surface of the aerofoil. As the aerofoil continues in the downstroke, this RLEV will move further to the wake, and there won't be any counter-rotating vortex pair or induced velocity effect, but there will be only a suction effect. Okay, so there will be only a suction effect of the RLEV, and because of that, this present stroke LEV and the suction effect of the RLEV, we think that this RLEV is having a higher strength compared to the LEV, so that may leads to a deterioration in the thrust, or by that a formation of the first peak happens. I'll come subsequently that this may not be the only region for this thrust deterioration. There are other regions attached to it. The one, if you remember, I have discussed about the rotational effect. Like when I go for higher flapping frequency, the rotational effect appears on the aerofoil, because the aerofoil needs to attain a higher pitching angle, okay, in the non-dimensional time, as we have discussed. So that effect will come into picture. So at this moment, just remember that this is one of the effect, the suction effect of the RLEV, and there will be further effects that will contribute to this thrust deterioration and attaining the first valley here, okay, and also which is a formation of the first peak, of course. Afterwards, you can see that the RLEV, actually this RLEV sets, and only the effect of the LEV is present, which is present stroke LEV, and due to that the thrust increases, like already we have discussed for previous two cases. As the strength of the LEV increases, the thrust increases and it attains a peak, and afterwards when the aerofoil starts the preparation for the next upstroke, it reduces its pitching angle. That's why the thrust, or the transient thrust, reduces. Okay, so this is already we have discussed. Now coming into what happens when we increase the flapping frequency. Like I have said, when we increase the flapping frequency, the thrust further reduces. Okay, it can go to the drag. So what is the cause for it? Here I have shown comparison for the two Strohal number, 0.4, and another one is for 0.5, two Strohal number, and keeping the angle of attack 10 degree. This same thing happens for other angle of attacks also. So just I have taken as a reference or representative case as 10 degree. So you can see that the drag producing region is quite large at higher flapping frequency. Okay, so the drag producing region here, you can see that is nearing to zero, but here it is in the negative side. So drag producing region is quite large. Before you go to the drag, you can see also another thing, the peak, transient peak also has increased in the higher flapping frequency. So the transient peak can increase because of the higher induced velocity and as well as higher LEV strength at higher flapping frequency, which is quite obvious from these pictures. You can see that if I compare for 0.4 and compare for 0.5, LEV strength in this case is larger. Also the induced velocity strength in this case is larger. Well, I did not show the quantitative information about the vorticity magnitude on the aerofoil in this slide, but we have seen from the quantitative magnitude also the induced velocity effects increases a lot, and this one LEV strength increases a lot. So now what is happening in this valley region? This is more important than just simply the enhancement of the transient peak. So in the valley region, you can see that the suction effect is one thing which is also pronounced, but you can see that simultaneously the LEV strength is also increased at the higher flapping frequency. So this doesn't look correct to us, like whether this is the only effect contributing for so much amount of drag production. So we felt it is not the case, but there may be several other things which might be contributing to it. So to investigate that, what we did, we tried to remove the effect of RLEV completely from our investigation. And that can be done if we just consider about the first flapping stroke. So at the very first flapping cycle, there is no formation of RLEV, because RLEV only appear when there is the LEV formed in the previous stroke. So in the downstroke itself, there is no previous stroke to it. So at the very first stroke, we don't see the effect of RLEV. Okay, so we remove the effect of RLEV and try to see how the profiles look like. So here I have shown a comparison between two Strohal number, and this is for the very first flapping cycle. Okay, very first flapping cycle. So like mentioned, first downstroke. So you can see the first downstroke also, we saw a negative type of or a valley region in both Strohal number 0.4 and 0.5, which is quite surprising to us then. Like there is no effect of RLEV, but there is still a drag producing valley region. So to further look into that, we found there is a significant low pressure region which is developed under the aerofoil due to a higher rotation of the aerofoil at higher flapping frequency. Like I have already said, in non-dimensional time scale, the pitching amplitude increases significantly. So to attain that larger pitching amplitude, the aerofoil needs to rotate significantly. Okay, so that's why this, due to this higher rotation, you can think about from the Newton's law, it will develop a low pressure region under the aerofoil. Okay, and that range of the expanse of the low pressure region under the aerofoil increases with the flapping frequency. Okay, so this is what is the main cause of this thrust reducing in the time averagicity, as well as on an average scale. If I this is the main cause for the thrust reduction on a transiency, and if I do a time average, then I will of course get a reduction in the time average value. Okay, so next, so after we know that what are the causes for the reduction in the propulsive performance at high flapping frequency, here I have summarized the drag producing valley region, then the low pressure region, and partly because of the RLEV. These three effects are coming to or contributing to the reduction in the time average thrust as well as in the transient valley formation, transiency valley formation. Now, if I want to increase this propulsive performance, like now we understood what is happening at a high flapping frequency, but how we can further improve the propulsive performance? Is there any way we can increase it? So our next task objective was to improve the propulsive performance at higher flapping frequency, like these arrows what I have shown here. We have looked into one of the previous articles by Howard, who have shown that by modifying angle of attack, the thrust behavior may be affected for the aerofoil, but the detailed investigation was not thorough in that. There was not much information about the flow structure and why we supposed to follow such effective angle of attack profile at the very first. So we thought of investigating from that aspect and try to provide an alternate solution. So the very first approach I will say here is there, like the question what we pose is it possible to enhance the thrust at high flapping frequency? If yes, then how do you do it? So we start with first approach by modifying the effective angle of attack profile. So previously our effective angle of attack profile looks like a sinusoidal one. Now we try to modify it to an alternate profile, like you have seen here. Basically, we have adopted two different profile. One is sinusoidal type, which I will say smooth trapezoidal profile. Both of these can be considered as trapezoidal or smooth trapezoidal profile because it has a base length here and two heights also. So a part of trapezoid. So we named it as a smooth trapezoid profile. One follows the sinusoidal type, other follows elliptical type. Okay, so the legs follows the elliptical type and sinusoidal type. And what is so special of following these two type of effective angle profile? So the aim is to reduce the rotation effect. Like previously I have discussed, the rotation effect is the main source for the thrust reduction. If you can somehow delay that rotation effect or somehow totally remove that, then we may get some benefit in the thrust performance. So that is what, when we checked the rate of rotation of the aerofoil for these two type of profile at the same Stouhal number. Like here the Stouhal number is, if I remember correctly, it is 0.4 or 0.5 for the same Stouhal number for the sinusoidal effective angle of attack and the our modified version. You can see a region here where you can see that is a sharp reduction or a reduction in the rate of aerofoil rotation. Okay, so this much amount of rate of reduction is sufficient for us to give or to generate good amount of increase in the propulsive performance. So I'll come to that subsequently. So detailed equations you can find out from our publication. I will not go through the these formulations here. Yes, so this is what we have seen, which is quite encouraging also. So the dotted line is for our previous investigation, we have considered here 15-degree angle of attack. You can see that this is what sharply it reduces with increase in the Strouhal number. But for a modified profile, you can see that we can delay the thrust reduction. Okay, first thing, and also the second thing is we can actually increase the thrust performance at the higher flapping frequency also, and particularly for elliptical type of profile we can increase it. And now we know how to increase, basically by reducing the rate of rotation of the aerofoil, by defining an effective angle of attack profile in such a way that its rate of rotation of the aerofoil reduces significantly at high flapping frequency, then we can get a thrust enhancement. So this work has been published in 2018. You can, if you are interested, you can look into it. Yes, so this was our first approach. The second approach, what we recently worked on, the second approach is to find out an alternate measure by changing, by following the same sinusoidal effective angle of attack profile, but modifying the pitching center on the aerofoil itself. Like previously we have studied the pitching or the both flapping, heaving and pitching happening on the pivot location B. Now if we can shift our pivot location to A, or towards the leading edge side, or C, or towards the trailing edge side, and by following the same sinusoidal effective angle of attack profile, that means this plot I think you have already seen previously. So we are retaining the same profile but modifying the pivot location. So by that, what we are trying to do is, by that we are trying to actually shift the rotation induced effects on the aerofoil to different locations. Okay, so you can see here on pivot A, if I compare different time step for a same flapping frequency at a different time step for 3 different pivot location A, B and C, at T star equal to 0, you can see that I get a larger surface velocity towards the trailing edge side and a smaller surface velocity towards the leading edge side. Whereas for pivot B, it is symmetric. Both, like on this side you get on the downward side surface velocity, on this side you get a upward side, and on C it is exactly opposite as pivot A. Okay, and same thing you can also follow for different time steps. So at T star equal to 0.05, basically the aerofoil has 0 acceleration because it is at the maximum point. Okay, so it changes its pitching pitching angle. From this side it starts to reduce, so that's why you are getting a symmetric or velocity distribution throughout the aerofoil surface. Okay, so we try to see what is happening in this case, whether it is beneficial or it can modify whatever we have seen the thrust reduction previously, by of course by modifying the rotation induced effects. So yes, so this is what we have seen. We found definitely the thrust performance is varying. In some cases the thrust performance is improved, in some cases the thrust performance is reduced. For pivot B, already what I have discussed at the very first, like this is what the pattern is, it increases and reduces, and these are the magnitude values which I have shown based on the red color line bar here. Okay, so if you compare pivot A performance, which is you can see the axis values are slightly different. I think they are same. So you can see that the performance for pivot A is better than pivot B. Okay, in terms of you can see the magnitude wise here. At higher angle of attack, basically it is more beneficial, and also it delays the critical Strouhal number to a bit. Like in this case, what we have seen, the critical Strouhal number looks like around 0.68 or 0.65. In this case, it is nearby 0.62. So it delays slightly, not significantly, but the values, the magnitude wise, it increases a lot. And whereas pivot C is not so beneficial, when your pivot location is towards the trailing edge side, it is not so beneficial. It is rather detrimental than pivot B itself. Okay, so this is what we have found, and we have submitted, and already the paper is accepted now. The details I will not go through. Like again, we have categorized the flow physics and all those information what we have discussed for the simplified case, everything we have discussed in this paper. If you're interested, you can go through. The idea is now if we can conclude from the present talk, the propulsive performance of the aerofoil is not same at different flapping frequency, I will say. With the increase in the flapping frequency, the propulsive performance gets modified. It increases up to a critical Stowell number, and beyond that it reduces, and the rate of reduction depends on different type of flow features, like whether there is a LEV, whether there is a TEV, which is telling us vortex, or there is a counter rotating vortex, depending on the flow structure. Okay, so depending on the flow structure, as well as the rotation induced effect, like we have seen for higher flapping frequency, the rotation induced effects are significant. So which are, and also adverse, they are not favorable, they are adverse rotation in this bit. So that leads to a thrust reduction at higher flapping frequency. And there are two different ways we can modify the propulsive performance, rather improve the propulsive performance by modifying the effective angular profile. That is one of the way we can do it. The other one is okay, there is a spelling mistake here. The other one is by changing the pivot location. If we can shift the pivot location from pivot A to pivot, from the midpoint towards the leading edge side, then obviously it seems to be beneficial in terms of the propulsive performance. Okay, so I think yeah, these are few of publications I've shown here, and yeah, few more. Okay, so I think I'll be happy to take few more questions. We have around 10 minutes left, so I'll be happy to take few questions. Thank you.
Thank you very much, sir, for delivering such a nice talk. The session is now open for participants. If they are having any kind of questions, they can ask. Yes, anyone having any kind of a question? Yes, any participant having any kind of question?
Sir, I have questions regarding.
Yes, yes.
Yes, please go ahead.
Sir, good morning, sir. Sir,
Good morning.
Yes, sir. Sir,
Yes.
I want to know that, sir, till which range the laminar flow is existing, sir?
Okay, so the whole analysis what we have done and the results what I have shown is completely laminar. Okay, and there are studies which shows up to Reynolds number of 15,000 or so, in that range you can safely assume your flow to be laminar. Okay, provided your flow condition and scenarios is free from different type of disturbance, it is safe to assume laminar condition up to Reynolds number of 15,000. Okay, so that's why we have carried out all our analysis on the laminar viscous model itself.
But sir, in fluid mechanics book, it is written that Reynolds number is less than 10 to the power 5 or 10 to the power 6 is till that point it exits laminar flow, and after that it will be in transient, and after that it will be in turbulent flow. But that is only I have some doubt that how till 15 lakhs or 10 lakhs that laminar flow is existing.
Okay, yeah, so I think one of the way to answer your question is laminar flow, the definition varies for different type of objects. Okay, so the one you have said, the figure what you have mentioned, it is for the flat plate. If you know about flow in a circular pipe, the laminar flow regime is quite less than that, around 2000, around 3000, at the max 2000, 3000, then after that it changes to the turbulent. So it is actually problem specific. When we are talking about whether the flow is laminar or turbulent, it is a problem specific based on the characteristics length, and it cannot be same, cannot be considered same for the different problems. Okay, for this particular problem what we are dealing in at present, it is found to be laminar in the form of experiments and as well as from various other studies. Based on the definition is based on the chord length of the aerofoil. Okay, so this is not a unique definition that you can say that the laminar flow happens up to 10 to the power 4, 10 to the power 5. Not necessarily. You can see that on the flow in a pipe, the laminar changes to turbulent in Reynolds number around 2000 itself. Okay, so it's a problem specific. Any more question?
Yes, any other participant having any kind of question? Yes, any participant? Okay, so I presume there is no question from participant side. Okay, then on behalf of Mechanical Engineering Department of ADIT, Constituent College of CVM University, I would like to thank Dr. Sunil Manohar Das sir first for accepting our invitation and delivering such a nice and a detailed talk on the propulsive performance of two-dimensional flapping aerofoils. So you have covered all the aspects of this very nicely. You have shared your simulation results related with aerofoils. I'm sure that would be helpful to some of the participants to carry out the research work in that particular domain. You're also having really good amount of publication in this area, and the simulation that you have shown how to improve the performance at higher flapping frequencies also really good. So thank you very much, sir, for accepting the invitation and delivering this wonderful talk.
Thank you, Professor Thakkar. It was a nice hosting me here. And in case any more doubts you have, like the students and the audience, please get back to me over my email ID. I'll be happy to clarify their consent, and we'll be happy to collaborate if someone is really interested in this area also. Okay. Sure. Thank you very much.
Thank you very much.
I wish you everyone a good luck and have a successful STTP. This one.
Thank you, sir. Thank you very much, sir.
Thank you.
There is announcement for participant. The second session of Dr. Sanjay Mittal, sir, Professor IIT Kanpur, will start at 11:45 a.m. So all of you are requested to join on time at 11:45 a.m. For the second session. Thank you very much, everyone, for your active participation in this first session. We'll see you all at second session that will start at 11:45. Thank you very much.